This is Arumugam. Today I am coming with a new concept, inductance. It's a new word. Okay, let us see what is inductance and types of inductance. See, in the case of inductance, already you familiar with the word inductor. Inductor is nothing but helical coil. Helical coil. So you familiar with the word what's it? Inductor. From the word inductor, I am going to introduce the new one, inductance. What is it? Inductance. Okay, let us see the definition for inductance. What is inductance? Inductance is nothing but it's a ratio of flux linkages to the current. That means flux changes in the coil to the current flows through the coil. That is inductance. That means L equal to lambda divided by I. The lambda represents the linkage, flux linkage, where I represents the current. So we can write lambda equal to what's it? N phi. Already familiar. The flux linkage is directly proportional to what's it? Magnetic flux. And also we can write N. N represents the number of turns in the coil. So finally we can write L equal to N phi by I. N phi by I. So very simple. The inductance is defined as the ratio of flux linkage in the coil to the current flows through the coil. This is a induction. This is a inductance definition. Okay, we can see some other information about the inductance. See the case of inductance, the self-induced EMF across an inductor, already familiar, Faraday's law. It's a self-induced EMF. EMF is induced wherever the flux changes in the coil. Am I right? The induced EMF is named as self-induced EMF, or it can be called as a back EMF. Sometimes they will ask in board exam what is back EMF. So back EMF is nothing but self-induced EMF. Already you familiar with the equation E equal to, what's the formula? E equal to minus L into di by dt. That means now only I introduce the letter L. L is a what's it? Self-inductance. The E already you familiar, E is equal to from the Faraday's law, E equal to minus d phi by dt. From that one we can derive the equation E equal to minus L into di by dt, where E for induced EMF across the inductor, L represents the inductance, its unit is Henry, and di by dt, there is a rate of change of current. Okay, here they put negative sign, minus sign. That means what's that? The negative sign indicates that the direction of self-induced EMF is opposes to the change in current. The induced current always opposes the change in current. Suppose the current flows through the coil and EMF is induced in the same coil, but the induced EMF opposes the flowing current. So that this is opposite. So we put minus, negative sign. For example, during the calculation, for the case of EMF, self-induced EMF calculation, the value of self-induced EMF should always be given a negative value. If colored E, the value obtained should have a negative sign. And next one, what's a unit of inductance? The unit of inductance is nothing but what's it? Henry. The inductance is measured by Henry. So next question arises, what is 1 Henry? Now define 1 Henry. Very simple. I told already definition for inductance. What's the definition of inductance? I told you the flux linkage to the current flows through that. The same way you can see a coil has an inductance of 1 Henry when the condition is when an EMF of 1 volt is induced when the current changes at a rate of 1 ampere per second. Clear? So this is a definition for the 1 Henry. 1 Henry. Okay. Let us see the types of inductance. In your syllabus, they discuss two types of inductance. One is mutual inductance and self-inductance. Mutual inductance and self-inductance. First we can see mutual inductance, and then later we will discuss the self-inductance. See, in the case of mutual inductance, mutual induction, what's that mutual induction? See the diagram and then I will explain clearly. See the diagram clear. First, there's a two coil is there, am I right? The one coil is first coil, second one is neighboring coil is a secondary coil. If V1, the first coil is connected with the V1. Here V1 represents the alternating source. Alternating source is the AC current is connected to the first coil. What happens if the current flows through the coil? Current flows in the first coil. What happens? Magnetic field will varies. Magnetic field will be varies. If the magnetic field varies, what happens? That will induce the EMF according to Faraday's law. Alright, where the flux changes, EMF induced. So the flux changes in the first coil will induce an EMF on the neighboring coil, that is a secondary coil. So the secondary coil V2 that shows the induced EMF due to variation of flux change in the first coil. This is called mutual induction. Mutually, that means what's that? Mutual means if the current changes or varies in one coil, an EMF induced on the another coil. This is called mutual induction. It's called mutual induction. Clear? See the next one diagram. So how do we define, or what's the phenomena for mutual induction? The mutual induction is the phenomenon of production of induced EMF in one coil due to change of current in the neighboring coil. So this is a definition for the mutual induction. Mutual induction. Okay. I can go for the next thing is coefficient of mutual induction. Coefficient of mutual induction is nothing but mutual inductance. Okay. At any instant, the magnetic flux linked to the secondary coil is directly proportional to the current in the primary coil. Am I right? See the diagram. The flux linked in the secondary coil. Flux linked with the secondary coil is directly proportional to current in the primary coil. So the induced flux depends on the current flows in the primary coil. So this is a concept. So magnetic flux linked with the secondary coil is directly proportional to current in the primary coil. So we can write phi is directly proportional to I is a common, or we can write phi is directly proportional to I. What about the phi? Phi equal to, you put some constant, that is m into I, where m is denoted as a coefficient of mutual induction or mutual inductance. So m is nothing but coefficient of mutual induction. And then from the equation we can go for the EMF. Right, now we know the phi. What's the flux changed in the secondary coil? If you know the flux change in the coil, you can calculate the EMF, how much of EMF induced in the coil. From the Faraday's law, you know that E equal to minus d phi by dt, or we can write, what's that? Phi equal to what's that? Mi, you substitute the value of phi in the equation. The m is a constant, so we cannot differentiate. You take it out, m, and remaining what's it? Di by dt. So E equal to minus m into di by dt. Clear? So this is the EMF induced in the mutual induction. In the same way, we are going to see the coefficient of mutual induction for the solenoid. Mutual induction for the solenoid. Let us see the diagram. There is a two coil is there. Am I right? There is a two coil. The two coil can have a common axis. The inner coil have the radius is R1. The outer coil have the radius R2. But outer coil have the radius is more than that of the inner coil. And the number of turns in the inner side coil is N1. The number of turns in the outer side coil is what's it? N2. But here consider the length of the both coils are having same value, that is L. For this type of coaxial coil, what's a mutual induction? Mutual induction for the coil 1 and 2. Okay, see, consider two long coaxial solenoid. Here I am going to derive expression for the what is the mutual induction for the long solenoid. Now let us consider the two long coaxial solenoid S1 and S2. The S2 wound over the S1, where S2 is wound over the S1. S1 is inner side, S2 is the outer side. Right. Let L be the length of the each solenoid. R1 and R2 I told already, radii of the two solenoids. A is the area of cross section of the inner solenoid S1, that is pi R1 square. And number of turns for the two solenoids like N1 and N2. First we pass a time varying current I2 through S2. First imagine the current flows through the coil S2. As the current flows through that I2 current. First we pass the time varying current. Time varying current is alternating current. Is passed through the solenoid S2. The magnetic field set up inside S2 due to I2, you know that. So what's the magnetic induction? B equal to, already familiar, mu Ni. Am I right? B equal to mu into N into I. So for the second coil, so B2 equal to mu naught N2 I2. Where N2 equal to, what's the number of turns? Where N2 is nothing but N2 by I, or number of turns per unit length of solenoid S2. The total magnetic flux linked with the inner solenoid. You want to calculate that magnetic flux linked to the inner solenoid S1 is given by, that is phi equal to BA. Already you know that I told you phi equal to BA, where n number of turns, so into n, B2 A into N1, or B already derived, what's it? Mu naught N2 I2. You can substitute the value of B2. So mu naught N2 I2 into A into N1. So mutual inductance of coil 1 with respect to coil 2 is given by, that is M12 equal to phi 1 by I2. Am I right? M12 equal nothing but phi 1 by I2. Now we calculate the phi, you know that. What's the phi? Mu naught N2 I2 A into N1 divided by, what's it? I2 divided by I2. So finally we can get, what's the formula? For M, mutual induction of a coil 1 with respect to 2 is mu naught N2 A N1 by I. Clear? Next, suppose we consider the flux linked with the outer solenoid S2 due to current I1, the inner solenoid S1. So the field B1 due to I1 is constant inside S1 but 0 in the annular region between the two solenoid. Am I right? See, one more thing, I consider the flux linked with the outer solenoid S2 due to the current I1 in the inner solenoid S1. So we can write B1. So just opposite to the first case. In the first case we calculate B2, here we calculate the B1. B1 is nothing but mu naught N1 I1, where N1 equal to what? You know that N1 by L, N1 by L, not I, N1 by L. So number of turns per unit length of S1, that is a small n1. The total flux linked with the outer solenoid S2 is, that is given by phi 2 equal to B1 A N2, or we can write mu naught N1 I1 A N2, or we can write mu naught N2 A N1 L1 by L. So mutual inductance of coil 2 with respect to 1 is M21. M21 is equal to phi 2 by I1, or we can write mu naught N2 A N1 by L. See, already we derived the equation, what's it? M12. That's a mutual induction of the first coil with respect to second one. But here we derived mutual induction of the coil 2 with respect to 1. If you consider the two equations, both are same. I mean M21 equal to M21 should be equal to M12, that is equal to M. So finally we can write commonly we can write M equal to mu naught N2 A N1 by L. Thus mutual inductance of two coil is the property of their combination. Right, from the equation, what's the conclusion? The mutual inductance of two coil is the property of their combination. It does not matter which one of the function as primary or secondary coil. Clear? So this is a equation of, let's say, mutual induction for the long solenoid. Maybe they will ask in the board question, board exam. Okay. Next thing, mutual inductance depends. See, what are the factors affect the mutual inductance? From the equation, you know that N is in the numerator. Am I right? In the equation, M is directly proportional to N. So, number of turns, larger number of turns also another factor for mutual inductance. If the larger number of turns, larger the mutual inductance. Next one, larger the common cross-section area. See, in the equation, mutual induction is directly proportional to area of cross-section A. So if the area of cross-section increases, the mutual inductance also increases. But the larger the distance between the two solenoids, the smaller will be the magnetic flux linked with the secondary coil due to current in the primary coil, and smaller will be the value of M. See, the distance between the two solenoid, the distance between the two solenoid is inversely proportional. So larger the distance between the two solenoid, smaller will be the magnetic flux linked with the secondary coil due to the current in the primary coil, hence smaller will be the value of M. Right? The larger distance between the two solenoid, that means that will give the smaller value of the M. Same way, from the concept, we can go for the one more problem. See, coil 1 of pair of coupled coils has a continuous current of 5 ampere and the corresponding fluxes phi 1 and phi 2 are 0.6 milliweber and 0.4 milliweber respectively. If the turns are N1 equal to 500, N2 is 1500, find L1, L2, M and K. You know that what's a K? It's a ratio. It's a ratio between ratio of phi 2 by phi 1. So phi 1 is given and phi 2 also given. Can divide, can get what's at 0.667. What is a M? Mutual induction. That is M equal to N2 phi 2 by I1. Okay, substitute the value, can get 0.12 Henry. What about the L1? What about the L1 self-induction? That is N1 phi 1 by I1. That is equal to 0.06 Henry. The same way L2. That is what? N2 phi 2 divided by I2. That is given by 0.539 Henry. Clear? So this is the way we can understand the concept of mutual inductance. So next we see the another one inductance, that is called self-inductance. Already I told you clearly, self-inductance is nothing but when the current flows in one coil and EMF induced in the same coil. See, one more time I tell you, if the current flows alternating current flows through one coil and EMF induced in the same coil. See, now only we discussed what's a mutual induction. When the current flows in one coil and EMF induced on the another coil, that is a mutual inductance. But here we discussed if the current flows in one coil, EMF induced in the same coil, that is called self-inductance. Okay, see the diagram first clearly. I explained only the definition. From the diagram we can see clearly. From the diagram what said, the coil is connected with the battery and a key. If the key is open, what said, no current flows through the coil. If the key is closed, current flows through the coil. When you close the key and alternating current flows in the coil, what happens if the current, alternating current means what said, they will vary its magnitude as well as direction. So the magnetic field will be varied. Due to the variation of magnetic field, the EMF is induced. This is based on, what's it, Faraday's law. So flux changes, EMF induced, but induced EMF is flows in the same coil. In the same coil. But only thing, the induced current always opposes the flowing current in the coil. This is called self-induction. See, definition for the self-inductance. I told already as a definition. When the current flows in one coil, alternating current flows in one coil and EMF induced in the same coil. Here also the same thing. They told that the strength of the current, as the strength of the current in the coil is changed, the flux linked with the coil also changes. So under these circumstances, what happens? An EMF is induced in the coil, EMF induced in the coil too. That means such EMF is called self-induced EMF, and this phenomenon is known as self-induction. See, same way, if you consider the coil or solenoid, where the length of the coil is L, the area of cross-sectional of the coil is A. Now, I current flows through that, what happens? And EMF is induced, right? The coil has the n number of turns. See, here I am going to derive the expression for the self-inductance for the solenoid. See, last time we derived the expression, what is that? Mutual inductance for the solenoid. But here I am going to derive the expression for the self-inductance for the solenoid. For the case of solenoid is nothing but such helical coil. See, consider the solenoid L. This is a solenoid connected to a battery, and A is area of the coil, a length L. L is length, N denotes the number of turns in the coil. What happened? See, as you close the switch, what's it? Current flows through the coil. That means from the Lenz's law, the loop resists a change in magnetic field. So magnetic field is caused by the current. In the case of inductor, resists a change in current. You familiar that, what is that? B. That's a magnetic induction. B is nothing but mu naught Ni by L. Mu naught Ni by L. And also you can derive the expression, what's that? Phi. Phi is nothing but B dot A. B dot A. See, B, you know that mu naught Ni by L. Into A means that is what's that? Magnetic flux. Magnetic flux is nothing but mu naught Nia by L. Okay. How do you call it the EMF? How do you calculate the EMF of the coil? That means induced EMF in the coil. The EMF induced in the coil is given by E equal to, already I told you, E is equal to, what's that? d phi by dt. d phi by dt. Where you know that phi, you can substitute and you can write the final equation, what's that? It may be d by dt of mu naught n square I A by L. But here, except current, the other things are constant, so you take it out. Constant cannot be differentiated. So we can write induced EMF, that is equal to mu naught n square A by L into di by dt. Di by dt. Or we can write the L. This is a self-inductance. L represents the self-inductance for the lung solenoid, that is given by mu naught n square A by L. So this is also notable question. They will ask in board question. Okay, next one we can see energy stored in the inductor. Energy stored in a inductor. What's the energy stored in an inductor? Suppose current flows through the coil. How much of work is done on the current for the flowing current in the coil? How much of work is done on the coil? That is the energy stored in an inductor. See, you know that the electrical power P in overcoming the back EMF in the circuit is given by P equal to what's that? You know the formula, power equal to current into what's that? E. That we can write P equal to I into what is E on the basis of concept of self-inductance. E represents L into di by dt, or we can write rearrange the equation dt, go for the left hand side. So P dt equal to I into L into di. Right. P dt is nothing but du, small value of the potential, that is sort of du equal to I into L into di. Okay. Here I am going to derive the expression for the energy stored in the inductor. Energy stored means what's it? How much of potential energy? Electrical potential energy stored. So what electrical potential is stored means what's it? The total work done while current is changed from 0 to its final value of, the work done while the current changed from 0 to final value, that is given by what's that? Integral over what's that? Integral between what's that? 0 to u for du, or I you know that what is du already derived, I into L into di. So substitute the value of du. L is a constant, you take it out, I di, the limit value from 0 to 1. So if you integrate, if you integrate I into di, what happens? X dx is nothing but x square by 2. Same way, I di is nothing but that I square by 2. So we can write u equal to, energy stored, total work done, that is u equal to 1 by 2 L I square. For the case of capacitor, already familiar, you derived u equal to 1 by 2 C V square. So for a long air core solenoid, the self-inductance is L equal to, now only derived, mu naught n square A by L. So you can substitute the value of L in the above equation. Finally, you can get what's the energy stored in a solenoid. That is, you familiar? What's that? U equal to 1 by 2 L I square. You know the value of L. That is what's that? L mu naught n square A by L. Substitute the value of L. We can get final equation U equal to 1 by 2 mu naught n square A I square by L. So this is a equation or expression used for calculate the energy stored in an inductor. Finally, we can see the factors affect the self-inductance, or in other words, the self-inductance L depends on, what are that? First one is size and shape of the coil. Size and shape of the coil will change the self-inductance. The number of turns also will change the self-inductance. The magnetic property of the medium within the coil in which the flux exists. So magnetic property of the medium also one of the factor in the case of self-inductance. But main thing, self-inductance L does not depends on the current. Does not depends on the current. See the equation which will self-inductance of the coil. Already derived the equation. Am I right? That is L equal to mu naught n square A by L. So this is the thing. See in the equation no I is not present. That means that is independent of the current. But L is directly proportional number of turns. L is directly proportional to area. Area means what said? Size and shape. And L is directly proportional to mu naught. So medium, with respect to medium. So this is a way we can discuss the factors affecting the self-inductance of the coil. Clear? Thank you. I hope you all understand about the mutual inductance as well as self-inductance. Clear? Okay, next video I will come with another one concept like AC generator. Thank you.